Hello, this is Mr. Bush. Today we're going to go over basically everything you need to know for the STAR test involving chemistry. So we're going to start off with our subatomic particles. There are three: protons, neutrons, and electrons. Protons have a positive charge, they have a mass of 1, and they're located in the nucleus. They also determine the identity of the element, which is why I put the ID by our protons. Neutrons basically have a charge of 0 or neutral, or think no charge. They have a mass of 1, and they're also located in the nucleus. The electrons have a negative charge. This is why you get basically the plus and minus sign on your batteries. They have very little mass, which is practically 0, and they orbit in the electron cloud. Alright. Now we're going to look at how this relates back to our periodic table. On your periodic table that you're going to use during the STAR test, the atomic number is basically marked. Basically, this is the number of protons. Since the number of protons determines the element's identity, each element has its own unique atomic number. Example there, silicon's is 14. Now, the atomic mass is the protons plus the neutrons, and the reason for this is protons and neutrons are the only subatomic particle that has mass. Now we're going to look at valence electrons and groups. Alright, the number under each group is the number of valence electrons. This determines how an element reacts. So basically, you look there under 17, you have 7A. That means every element in that group has basically will have 7 valence electrons and will react the same way. This is true for every single element as far as, let's say, fluorine, chlorine, bromide, iodine. All of them will react the exact same way. Alright, let's go ahead and look at periods. Now, periods basically go sideways. So you have 7 different periods here. And they determine the number of energy levels. Basically, if it is in period 3, it'll have 3 energy levels. If the element, let's say, is in period 4, it'll have 4 energy levels. And we'll show you a real quick example of that. Alright, if you look here, chlorine is going to be in group 17, and it's going to be in period 3. Because it's in group 17, it'll have 7 valence electrons. And if you look on the outside ring there are basically 7 valence electrons. Now it's going to be in period 3. Basically going sideways over here, it's going to be in period 3. And if you count, there are 3 different energy levels on this atom. Alright. Basically, that's what groups and periods mean. Let's go ahead and move on to our next topic. Alright, now we're going to look at the 4 signs of a chemical change. And our best signs are a gas is produced. So anytime you see bubbling, that's a sign of a chemical change. Color change. Basically, if it was start off as red and turns to blue, that's a sign there's been a chemical reaction. Temperature change. That's either getting colder or getting warmer. And last, a precipitant. This is when you mix 2 liquids together and it produces a solid, typically causing it to drift down to the bottom. And the best sign is if you produce a new substance. If you see any of these, you know you basically have a chemical change, and the chemical properties of the substance should change during the reaction. Alright, let's go ahead and look at the difference between compounds and pure elements. Alright, a pure element is made up of only one type of atom. As you can see at the examples at the top, each one of those molecules has only one type of atom. Like the first one is just hydrogen atoms, second one is just oxygen atoms. A pure element has only one type of atoms. A compound has 2 or more elements and they're bonded together. So if you look here, basically for each one of these compounds, the different elements are bonded together, and when you have 2 elements, basically different elements bonded together, it changes the properties of both elements. We're going to go ahead and look at a real quick example of that. Alright, my first example, we're going to basically use water. Water is a compound that is made of hydrogen and oxygen. Hydrogen is an explosive gas. It's used in rocket fuel. It's very, very light. Oxygen is about 22% of the air that we breathe. It's flammable. Basically, fires need it to burn. Water is not a gas. It's a liquid. You can't breathe it. It doesn't help things burn. Basically, it has different properties than the elements that make it up. So anytime there's a chemical reaction that produces a new compound, the compound will have different properties than the elements that make it up. Alright, just going to repeat that one more time. Different properties than the two elements that make it up. And this is true for every compound. Alright, let's go ahead and move on to our next topic. Alright, we're going to go back over how to read chemical formulas. The first thing we're going to look at is a subscript. A subscript tells you how many of that element is in a molecule. For example, this 3 means that there are going to be 3 Ks or 3 potassiums in that molecule. This 4 means that there are going to be 4 oxygens in that molecule. If there's no number, then that basically means that there's only one of them. And the reason why scientists did that is it's a lot easier to write no number than having to put a 1 every time there's only one element there. Alright, let's go ahead and look at what a coefficient is. A coefficient is the large number that goes in front of the entire formula. It means you're basically having 2 of the entire thing, or whatever coefficient is in front of it. Think of it kind of like in math. Basically, it's like putting a parentheses around the entire compound, saying I have 2 of this entire thing in my formula. And the real easy way to solve these is basically you just multiply 2 all the way across. So you get 2 times 3, giving you 6 total potassiums. You'd have 2 times 1, giving you 2 phosphorus, and 2 times 4, giving you 8 oxygens. I'll go ahead and show you another example of this real quick. Alright, this is a methane molecule. If you look here, it basically has 1 carbon, because there's no number behind the carbon. There's no coefficient there, or subscript. You look here, it will have 4 hydrogens, because it has a subscript of 4. Now if I put in a coefficient of, let's say, 2, it means I have 2 of the entire thing. Alright, well, sorry about this. It would not let me copy the picture again, so instead I drew a very poorly drawn methane molecule. Basically, by putting the coefficient in front of it, you have 2 of that entire molecule. But as you can see, basically they're not bonded together like they would be if it was like C2H8. Alright, let's go ahead and move on to our next thing, balancing equations. Alright, basically what you start with is going to be your reactants. Everything on the left side of the arrow is going to be reactants. Everything on the right side of the arrow is going to be your products. Kind of similar to in math. Basically you end with your products, and in the beginning think of it as it has to react, or whatever is reacting, that's going to be your reactants. Now, the first step to a balancing equation is you write down basically the elements on each side. Then you go through and you count the number of each atoms. Basically that coefficient there, the subscript there means you have 2 nitrogens. You multiply the coefficient by the subscript and you get 6 hydrogens. Then you go over here. Basically you do the same thing. 2 times 1 gives you 2 nitrogens. 2 times 3 gives you 6 hydrogens. And if it's equal on each side, then it's balanced. If it's not, then it's unbalanced. And that's going to be the law of conservation of mass, stating that basically you cannot create or destroy mass. During a chemical reaction, the elements or the atoms you start with, you have to end with. Basically, during this entire reaction, none of the elements were created or destroyed. Instead, you just rearranged the atoms. You took these two nitrogen atoms and rearranged them so that they're bonded with these 6 hydrogens. So the key thing on this is, if you have the same number on each side, it is balanced, and that would work. If you do not have the same number on each side, it's unbalanced, and you would have to rearrange the equation because you cannot create or destroy mass according to the law of conservation of mass. Our last topic, I forgot to do this with the periodic table, is going to be metals, nonmetals, and metalloids. Alright, your table is basically divided up into these 3 things, metals, nonmetals, and metalloids. Everything to the left, with one exception of hydrogen, is going to be metals. If you get confused and you can't remember, find a metal that you know, like iron or copper or let's say gold. Once you find one of those, that's the side that's going to be metals. And then the right side over here is going to be your nonmetals. Kind of like oxygen. You all know what oxygen is. You breathe it every day. So if you see oxygen, you know that that side is nonmetals. And everything in the middle is kind of like a metalloid, is in between both. It can have properties of both. So let's go ahead and look at that real quick. Now, for your metalloids, the way you find those is basically anything that has 2 sides touching this staircase going down the middle. I like to call it the iron curtain because it separates your metals from your nonmetals, but you can come up with your own name for it. Basically, anything that has 2 sides that touch that is going to be considered a metalloid, with one exception. That's going to be aluminum, because we all know what aluminum is. It's in aluminum cans, aluminum foil, and it has all the properties of a metal. So anything that touches with 2 sides is going to be a metalloid, with the exception of aluminum. Let's go ahead and look at the properties of metals and nonmetals. Alright, here are the properties of metals. Basically, they're shiny, they're good conductors of heat and electricity, kind of why you would not want to put a metal wire into a light socket. Also, it's why we make, most cords have copper on the inside to conduct electricity. Pans are made out of metal to help conduct heat. Malleable basically comes from the Old English to hammer, or basically to hammer it flat. It means that you can hammer it without it shattering. It bends instead of breaking. Ductile means you can basically bend it. You can pull it into a wire, like a copper wire for like cords or electrical work. Now, nonmetals are the exact opposite. Their luster is going to be not shiny. It's dull. They're poor conductors of heat and electricity, and the other name for that is going to be a insulator, kind of like the plastic on the outside of a wire. That's to keep you from getting shocked, because it insulates and it keeps the electricity from going through it. Not malleable basically means, is another name for that is going to be brittle. If you hit let's say a piece of glass, a rock, something that's a non-metal, with a hammer, it's going to shatter before it bends. And the same thing, they're not ductile, they're brittle. They'll shatter before they bend. And a metalloid can be a combination of the two. Like it could be brittle, but also be a conductor. Or it could be shiny and a semiconductor, meaning it kind of conducts electricity, but not very well. Alright, hopefully this was helpful, and y'all have a great day.